Just let me know when you're ready. I see it's recording. Okay. So welcome to the first regular WRS Twin Cities Water Resource Science seminar. And our seminar today is being given by Xiang Li. He's a PhD student. He just finished his master's this last summer and PhD student in the WRS program. And what he'll be talking about is the combining, I guess, of big data methods with physics and applying it to some watersheds. So I think that the big data analysis methods, machine learning methods, artificial intelligence, and so on are gaining ground in the hydrology, aquatic sciences, as well as in medical fields, biology, and so forth. And there's some real opportunities, I think, for students to learn a lot about how to use some of these methods. And in August, there was a workshop that was being sponsored by the National Science Foundation through a project here at the University of Minnesota. That is, the PI for that is Dr. Vipin Kumar in computer science. And there were several sessions. One of them dealt with aquatic sciences, one with hydrology, and one with atmospheric sciences. And Xiang, along with some other graduate colleagues of his, made a presentation similar to what he'll talk about today. His presentation will cover a bit more than what he talked about at that meeting. So I'll let you get started, Xiang.
Yep. Yep, great. Can everyone see my screen now?
Yes.
Yeah.
Yep, great, thanks. Yeah, like Dr. Neighbor just introduced, I'm Xiang Li, the current PhD student at WRS program, and I'm pleased today to introduce this topic, physics-guided deep learning models for hydrology, to us. And this, as Dr. Neighbor just introduced, this is one of the topics that's been discussed in the workshop held in August. And today I'm gonna reintroduce this for us, and also have some more content to introduce besides that. Yep, as a brief introduction, for physics-guided deep learning in hydrology, there are lots of tools and schemes we want to approach, and we'd like to use the stream flow as a critical variable for tackling this problem, as the stream flow is pretty important for water resource management and flood and drought prediction. And as hydrologists, we'd always like to approach stream flow by using physics models and hydrological models, but physics models had numerous challenges for modeling stream flow, as the difficult model calibration and not a comprehensive understanding about stream flow generation. And then under this big data era, the machine learning tools and data science techniques are becoming way popular these days. And the scientists from domains instead of hydrology would like to implement those tools to tackle real world problems. But those forms a new regime called data-driven methods. But data-driven methods alone cannot address some challenges, especially in hydrology, like for the stream flow prediction, because they always need a large amount of training data, and they argued that they are in lack of generalizability to out of sample scenarios, because the models being trained from data-driven approaches are based purely on data instead of physical principles. So therefore, the physics-guided deep learning is an approach to complement physics models and deep learning models, the ability from this tool to try to approach the same goal, which is the prediction of the target variables. And in hydrology, one of the most important hydrological variable is the stream flow. And as I just said, where as hydrologists and graduate students or later going to be researchers for water domains, we know that water cycle is important. The hydrological cycle forms every basics about water generation, but it itself has some certain challenges. So is there some way that under this big data era and machine learning era that we could use some tools that's not being used in hydrologic domain to improve the stream flow prediction? And give us a brief overview about the terrestrial hydrological cycles and how stream flow is formed. This slide shows a basic and a general physical mechanism for discharge generation. As to model and understanding our hydrological cycle as in one framework, the drivers for the stream flow generation includes meteorological data like the wind speed, the relative humidity, temperature, and solar radiation. And we also get the precipitation for driving all of the hydrological cycles. And the stream flow will be generated not only from precipitation, but also from other hydrological hydrological variables, such as the surface runoff, lateral flow, and base flow. And they all flow into stream channels via different pathways in a terrestrial water cycle. And we also know that not only from that, the evapotranspiration and the snow and the soil water, they all play a very important role for regulating the stream flow generation, because they are the important memory and storage of the Earth systems. And the dynamics of snow and soil waters, they are important to impact the stream flow in a way that we might not know it if we don't. We might not know it because we might not know it if we don't have hydrological domain knowledge. So that's how what we came up with the stream flow prediction when we have strong hydrological domain knowledge, and we like to tackle the stream flow prediction problem. But when we talk about this problem to computer scientists, what are things that coming out from their perspective, from their mindset? This slide shows a deep learning view about stream flow prediction in a computer scientist mindset. They like to approach this problem just like a computer scientist. They write code. They like to know the input and output of this problem. So in this case, the input will include the weather variables, and the output is the stream flow. And the models, from deep learning perspective, is like a black box or a functions that they're trying to come up with and to design. And they include, and specific to this case, since the stream flow is a time series data, to tackle this type of data, the machine learning architecture that's widely used for this type of data is the recurrent neural network. Some variants of recurrent neural networks are LSTMs or GRUs, etc. You might not have heard of it, but that's okay. It's just some terms I like to introduce that what the stream flow prediction task is for a deep learning perspective. And the key ideas in this case is to model the hydrological fluxes as part of deep learning framework, and to incorporate physics rules that's governing the hydraulic process involved for stream flow generation. And this slide shows something in detail, shows the details about that physics guided deep learning. If we don't know any physics, we just like to map or just feed in the model with the weather variables, and the output of the RNN, in this case, recurrent neural network, is the stream flow. It's like a black box. You just feed in the weather data, and the model itself will know how to deal with it. And another thing, if we know a little bit about physics, we could know that there are certain state variables that connecting weather and the stream flow that shall not be neglected, such as the soil water and evapotranspiration. And then another another framework, if we want to incorporate more physics into this world, is we like to not only fit in those variables, we like to use machine learning to model those hidden and important hidden variables that's play a very important role for stream flow generation because they existed in the hydrological cycle. So we model the states or fluxes as part of the machine learning architecture and use those predicted hidden variables to fit in the next variable, to fit in the next layers of the machine learning models. And this way they're designed in a hierarchical way that corresponds to how weather data are linked to stream flow. And I know that it might be too much to soak with deep learning models because it's brand new and pretty popular these days. But but as a metaphor of it, I'd like to give us some background and such that you won't be afraid of hearing the word of deep learning or machine learning because those are words that's being widely talked and discussed these days. I think a metaphor of deep learning is, we could assume it's like a linear regression. And I listed it on this slide showing how linear regression could be a metaphor to deep learning. In deep learning, there are usually three basic forms to fundamentally to form a fundamental knowledge of it: the architecture, loss function, optimization. So these three perspectives could also break down linear regression in this way. The linear regression maps the input, like the x, to a y, and it's in a linearly, and they are linearly transformed. And the parameters are involved, in this case, involve just the k in this slide and b. The k is a weighting matrix and b is a bias term. And deep learning networks is also just like that, because mapping x to y. But the deep learning model just makes that linear transformation way, way complex to fit in different types of data. And the loss function is how we want to train this model, like how do we want to find the k. And in linear regression, it usually could be RMSE, the root mean squared error quantifies how the predicted y deviates from the truth data. Because although we have formed the architecture of linear regression as y equals kx plus b, but how to find the k and b, assume that we only know x and y. So we might iterate, there are multiple options of k and b, but the best of that will be the one with the lowest loss function, which in this case, lowest RMSE. So how to find it forms the third regimes, which is the optimization. How to find it, and there are multiple ways to do it. It involves mathematics and statistics, like the gradient descent method. They will try to have a first guess about k and b, and then iterate through to see if there's any chance that k and b could improve such that the final loss function will be lowered, which means that the predicted y is approximates to the truth data. And that's after that metaphor about deep learning to linear regression, I'd like to introduce the next ideas, which is another way to incorporate physics into deep learning. We call it physics-based loss. Just like the RMSE in linear regression, we're just comparing about predicted discharge to the observed discharge. We are trying to make the deviation between these two as small as possible. But that's from a pure data perspective, because we know we are predicting stream flow. We like to predict the stream flow to be as closest to observe the stream flow. But if we want to take a physics principles into this case, there will be physics principles in hydrology, which is the water budget, that conserve the mass of water across the terrestrial hydrological cycle. So in this way, this is another way to approach physics predict learning, such that the trained recurrent neural network, not only will the stream flow predict the stream flow be as close to observed stream flow, it will also preserve the physical systems principal rules, and in hydrology, that is the conservation of mass. And for this talk, our research team are still designing the loss function for that to account the mass balance equation. And what the results I showed today might not include that because we are still doing research for this. And all of the intermediate variables, like those states values, are learned individually. And we implement this approach using synthetic data coming out hydrological model called the SWOT model for one of the watershed in southeast Minnesota. It is the South Branch of the Root River at Garden Meadow. And the input to the SWOT includes it is a synthetic data set. The input to it includes the synthetic precipitation, minimum and maximum daily temperature, humidity, wind speed, solar radiation, just like weather drivers to drive the terrestrial hydrological cycle. And the output from the SWOT includes the stream flow and other intermediate variables like the snow cover, soil water, and evapotranspiration, because we like to have some reference values to train the machine learning models. And our goal is to emulate SWOT using machine learnings to predict stream flow from those weather inputs. And on the right corner of this slide shows how that recurrent neural network was being implemented for tackling this task. And LSTM is one variant of the recurrent neural network. And there were some hyperparameters I showed on this slide, and they're how this initial LSTM was designed. And for some experimental settings, they used first 120 years for training, last 80 years for testing. And those parameters are how the LSTM was configured. And this slide shows some results. We modeled the stream flow, and on the first row we didn't consider any physics, just a pure LSTM models. We have only input and want to approach that when I want to predict stream flow. And the second one, we model the hidden soil waters we model the soil water from the LSTM and use that as input to the next hierarchical layer of recurrent neural network. And the third row incorporates not only soil water, but also snow cover. From the result, the model was trained using the RMSE as loss function. And when evaluated the model robustness, we used the natural cyclic efficiency metric, which is one widely used hydrological metric for evaluating hydrological model simulation and observation. We could see that the training and the testing NIC is increased when hidden states like the soil water are incorporated. It increased from 0.6 to 0.7 in training period, and also in testing period, it shows some satisfactory performance improvement. And furthermore, when not only soil water, but also snow cover was being modeled and taken into the recurrent neural network, the NIC also improves. And to have another background about NIC, if NIC is, when NIC is close to 1, it means the model performance is more satisfactory. So the reason we bring the soil water and snow cover into the recurrent neural network is we know that in hydrological processes, they are pretty important hidden states variables, but if we don't feed them, it's not how it is just a pure data-driven approach without considering physical principles, because the LSTM or other recurrent neural networks, they are designed in a way to tackle the natural language processing applications. Just like when we type in any words from our keyboard, to the computers and algorithms will give some prediction about what the next word will be tapped. So that's how the natural language processing application is being tackled by LSTM. but the way LSTM was designed hasn't considered physical principles in hydrology, because in our case, we'd like to predict the stream flow. And from the experiment we just conducted and it's like the results I show, we could find that the memory and storage at the beginning of the sample could boost the prediction performance. And this slide shows soil water dynamics. And this slide shows the snow cover. Snow, since especially in winter periods in Minnesota, the snow will be accumulated, and the snow will be accumulated. Then the stream flow generation schemes in summer and flooding seasons that the precipitation impacts stream flow most significantly will not be observed in winter periods. So the snow cover and the snow mechanism becomes another mechanism that has to be incorporated into stream flow prediction. And that is one important process that have to be included in addition to the data-driven approaches. The precipitation will become snow below zeros, and the snow melt occurs above zero. And this slide gives some physical interpretation about the machine learning models, because so far, even for computer scientists, when they implement machine learning models, they might not have a good understanding about why this model works. The way they design animated research, it mostly is trying to design architecture, and if the model prediction is more accurate, then that will be a very good, machine learning architecture. However, another research regime, either not only from not from hydrology but from computer science, is trying to interpret this black box machine learning models, because it has been argued that if we just train the model, feed in lots of training data, and we don't know what's going on there in that black box, we are afraid to use and implement those machine learning models. So to tackle this, so in our case for the stream flow prediction, we also give the physical interpretation about machine learning models. And here the hidden features are just some vectors in high-dimensional space of the machine learning models. And we plotted a few of them, and we shall know that for these machine learning models, and we did implement multiple recurrent neural networks for just the stream flow prediction. And we have, by the time we haven't explicitly fed the machine learning model with the physical important hidden features like the soil water and evapotranspiration or snow cover, we didn't find, we could still find there are reasonable agreement between certain hidden features and snow and soil water. So it means even when we train the machine learning models, we don't explicitly feed those variables, and we just let models say, we give you the weather data, and you're gonna be optimized to find the good parameter size to achieve a satisfactory performance about stream flow prediction. There are certain features that's automatically being learned by the model itself, which is in a reasonably consistency with the snow and soil water. It is a very interesting scenario, interesting case to observe. And as a summary from what I just introduced, the LSTMs, one variant of recurrent neural network, have shown the promising results for modeling stream flow. And when we, as a step-by-step experiment, when we introduce soil water and snow cover to the architecture, it improves the performance. And because we know the hydrological knowledge has been borrowed for the stream flow prediction, because the stream flow estimation has to incorporate some storage state variables. And just let's take some step aside from this. Not only for stream flow prediction in hydrology, there's also a very widely discussed topic to tackle, like the predictions in ungauged basins. Is there so far the experiment we did was just train a machine learning model to tackle one single basin. Is there some possibility that we could train a global model, but accounting for basin similarities, and generalize the streamflow prediction across different basins. And under this big data era, there's a whole bunch of data set being collected and being put into the repository. One of them is in hydrology community is the CAMOS data set. It's catchment attributes and meteorology for large sample studies. It collects all of the streamflow data and weather forcing data across the United States, and all of the data are collected and being prepared in a good format. They reflected a very densely distributed monitoring gauge network. This data set also includes hydrological simulations. And this data set was created in 2017 and it is totally online available for any researchers to do hydrological research. So just to point out that for this big data era, what big data era means for researchers and also for not only graduate students and also for undergraduate students, that there are lots of tools and data available for us to use and play around. And this is another technique. This is another variant about the LSTM I just mentioned. And this was designed by the Kritzer and Nearings. This is a paper published in 2019 to tackle the question that how to build a global model to learn basin similarities. In addition, they show some improvement by using in addition to an easy and a straightforward implementation of LSTM, they built another variant of LSTM called EA-LSTM, the entity-aware long short-term memory networks. What the difference from EA-LSTM and LSTM is how the data was fed in. Before, the input data was just the input data for a single basin just includes weather data for the specific basin. But if we could collected more catchment attributes for that basin and also feed in those catchment attributes to this LSTM, will the LSTM automatically learn how the streamflow in this specific basin responds different from others as a way to approach basin similarities or basin dissimilarities. And to implement this in Kritzer's paper, they feed in the time-dependent variables, which are weather drivers, and also the static features, basin similarities. They don't change a lot of time, because the interest for this implementation is to see how basin varies with each other. And we are interested to the spatial similarities instead of temporal trend. And this slide shows what those details about what those weather inputs and static features are. I just listed here just in case later we might want to go back to this slide. And now this slide is overall performance evaluation about the EA-LSTM prediction for the CAMOS data set. We could see that when we build a global model, this global model could get a satisfactory streamflow prediction performance across the United States. The streamflow prediction at different basins are different, but most of them are in a pretty satisfactory range. As long as they're above 0.5 or 0.5 and 0.6, they're redeemed as a satisfactory model prediction. But still, we could observe that there are gauges or basins that the EA-LSTM is not good at. So it shows that the limitedness of this EA-LSTM architecture, how it could be used to predict a streamflow. There is some limited about architecture itself. And just to show, but still, it's an improvement to account the basin similarities. And this slide I just showed how good EA-LSTM could be designed and implemented for streamflow prediction. For one of the gauging stations in Oregon State, the watershed is so 1,700 square kilometers. I just plotted how the model, how the EA-LSTM predicts the stream flow. And we could say it's pretty consistent to the observation. Which is a very satisfactory result. But there are still other cases. This is one of the other cases that shows unsatisfactory result. This is one of the basins in Arizona in a pretty arid, arid climate change, arid climate scenarios. The NSE in this case is negative. It means that the EA-LSTM does not reach a good prediction performance. It's not even good as the mean of the prediction. So overall, it's what this topic about this EA-LSTM for tackling the stream flow prediction is to give us an ideas and a view about what the current progress have been made for stream flow prediction. There are increasing interest for implement those data science tools for tackle domain problems, and there has been already a lot of research to do this, and it becomes more and more popular to use deep learning tools to domain-specific questions. And in hydrology, I use the stream flow prediction for explaining these ideas. But and our research and my research group are still tackling this program and tackling this problem and trying to solve it later, and by considering more and more physics into the stream flow prediction task. So in the future, what we propose to do is to learn other variables in a hierarchical multitask learning framework. Multitask learning framework is another regime besides just the classic deep learning, and it could help address the stream flow prediction task, and as we see it as another thread to pursue later. Then, as we mentioned, the mass balancing equation to constrain variables are also important, because in terrestrial hydrological cycle, the water amount has to be preserved. And also, we'd like to explore all other new ways to model storage or memory variables and generalize across more watersheds. And that's it. And I'd like to thank my colleagues and from the computer science department and the Pennsylvania State University. We had a very closely cooperation every week to pursue these ideas about cooperating physics into deep learning to tackle hydrological problems. So that's it. Thank you.
Thank you, Xiang.
Yep.
Let's see if there are any questions from anybody.
Yeah, I had a question.
Mm-hmm.
So does the SWOT model you use incorporate land cover or vegetation data in any way?
Yep. The SWOT model, we incorporate land use, and let's see what else. We incorporate land use and other raster data for implementing that, because it has to, for implementing SWOT model, it has to include those perspectives.
Thank you.
Yep.
Go ahead, Philip.
Mm-hmm.
So was there like similarities in the basins that it didn't model well, or was it just kind of random scatter for EA-LSTM?
Yeah, there are some patterns that because the basin behaves differently, although we are talking about the discharge generation, but the discharge generation mechanism across different basins are different, and the characteristic of basin might be used could be accounted for that, like the climate regimes, like in arid basins, the stream flow response of the basin will not be as that active and fluctuating as the flashy basins. So there are some similarities or dissimilarities across basins that might not be or have not been well modeled by the EA-LSTM, and it's along that track how to account for basin similarities or dissimilarities is a next pretty interesting topic to pursue.
Thank you.
Yep.
Say, I have a question about your mass balance.
Mm-hmm.
So if you have a couple of different states,
Mm-hmm.
say the soil, water, and the snow cover,
Mm-hmm.
and you're trying to adjust everything in an iterative fashion using your conservation of mass,
Mm-hmm.
how exactly do you decide how much to change the soil, water versus the snow cover? Is it all kind of just random guesses about which direction and how much to change, or is there some physics behind that as well?
Yeah, that's a very interesting topic. That's a very interesting question. And the way I think there are lots of experiments could be conducted to tackle that, because the machine learning we are trained, the design of loss function is aimed to force the machine learning model behave more consistent to physics. And like you said, the different storage terms there. If we want, there will be multiple tracks to tackle that. Either the soil waters or evapotranspiration. But what loss function did is if we predefine the loss function in a form to follow the principles we'd like to approach, it will automatically using the mathematical gradient descent method to adjust model parameters such that they are trained in a way to follow the principles we wanted to do. And so far, the loss function, in this case, the conservation, just incorporates precipitation, evaporation, discharge, and storage. We used it as a whole to conceptualize the hydrological memory systems of a basin. And we'd like to start it from a simple physics laws, the overall storage and later for the soil water storage, we could put more detailed context to that. But in that case, the models being trained will be expected to have a more consistent performance regarding the soil water. Does this answer the questions?
Yeah, thanks.
Yeah.
I just had another question. How many hidden layers do you actually use in your modeling? And how do you decide the number of hidden layers to use? I mean, one of the drawbacks for this type of modeling is that you can overfit if you use too many hidden layers.
Right. That's a very interesting and pretty important perspective about machine learning implementation. And the hidden layers we use so far are pretty simple. We just use two layers of recurrent neural network in this hierarchical structure when soil, water, and snow cover are incorporated. The first layer will predict the soil, water, and the snow cover, and the second layer will take what comes out from the first layer as an input. And they in addition to layer, I think another question is specifically for recurrent neural network is the hidden features. Hidden features, which means how the number of high dimensional space that we maps the input data to. In this case, we use the 28 hidden features as to map the input data to the high dimensional space. And that question about overfitting is also important that any machine learning implementation has to be aware of. And the way we tackle that is to use cross-validation. And in addition to make the model, in addition to the fact that we make the model not so complex, because the reason we decided the 28 hidden features is we did some experiments, and this one is reached, and this number of units is explored, is reaches to the most satisfactory performance, and when evaluated the model on the cross-validation, the training error and the testing error are not that different. Because if overfitting scheme is observed during implementing machine learning, it means that the training error is small, but the testing error is pretty huge. So in this way, we tackle it by selecting the parameters and the model architecture in a way that the training error and testing error do not deviate much.
I'll ask you a question about the taking into account the physics, you know, the way that it's being done here. It seems like it's an implicit way to handle it rather than an explicit expression of mass balance, such as P minus ET minus Q is equal to, you know, delta storage or something like that, which would be conservation of mass. Is that, am I interpreting that correctly? That you're not imposing conservation of mass explicitly in the network somehow, but it's more being done implicitly?
So far we haven't. Yeah. So far the current progress, at least the result I show here, hasn't incorporated this physical loss function into machine learning. And in the future, what we're gonna do is let's say if we want to incorporate physics-based loss into the function, into the machine learning task, we'll have to explicitly let the machine learning knows that under certain depth of these neural networks, that the neurons have to behave consistently compared to physics laws. So that's something in the future we're gonna do and implement to consider this physics laws. But it has to be explicitly designed and forced to let the machine learning system know that what behaviors it shall be penalized, what behaviors it shall be given more credits to.
Any other questions? I guess what I would ask one more question. This answer doesn't have to be very detailed, but you know, there's been some comment that I heard recently that maybe the machine learning people are going to overtake all the domain people. So hydrology will be run by the computer scientists, aquatic sciences will be run by the computer scientists, blah, 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 et cetera, et cetera. Doctors will be outrun by the computer scientists, you know, their opinions or their assessments of medical conditions. So is there a concern for all of us domain scientists that this might happen?
Yeah, that's pretty interesting, but I don't think there will be any chance that domain scientists will be replaced by just the machine learning algorithms or those computer science architecture, since the knowledge itself, like in computer science, from computer science perspective, the implementation of machine learning architecture is they are deemed as satisfactory as long as they reach to the goal that the predicted variables are pretty near or close to the observed variables. The question is, it doesn't mean it's knowledge. The architecture itself is designed in a way to approach this prediction task. It doesn't mean knowledge. But for domain scientists, we have our own language in hydrology. Like when we're gonna have the ideas from the weather drivers to stream flow. We know that the soil water is important, and the efforts and research we did is to understand this hydrological process. And every time when we find some principles are followed or being violated, we know there are some interesting patterns, and we researchers put efforts to understand those physical processes. But if we just use machine learning algorithms to tackle this, they might not even know what things going on there. They might not even know what state variables are. They just being told to train the model and design architecture without knowledge. But that is not how to achieve a good understanding about the system or I shall say a comprehensive understanding about a system.
That's good to hear, because even though I'm close to retirement, so I'm not worried about myself, but I want all of our young hydrologists and aquatic scientists and biologists to make sure that they know that their future is secure. So that your comment helps a lot there. And you're coming from the perspective of a hydrologist as well as computer science minor. So you have a pretty good idea of this, I think. Are there any other comments or questions? I would like to say that later in the semester we have another presentation that will actually just be a recorded video from that workshop and that occurred in August, but it will cover the topic of aquatic biology. And so I think that, you know, this would capture the interest of another group. Maybe a lot of people from Duluth possibly will be interested in because of the Large Lakes Observatory. But the interest in being able to model aquatic ecosystems, the chemistry and things like that, machine learning is being applied to that by cooperating with the domain science, or cooperation between domain scientists and big data science. So I think that that'll be interesting. I don't recall the date for that one, but it's out in October or something, I think. So. All right, David, is there anything else?
No, I think that was a great seminar. It's the clearest explanation I've ever heard of how PGML works. So I really appreciated that.
Yeah, thank you very much.
Yeah, sure.
All right, so I think that we're probably done, David, now.
Yeah, thank you, everybody.
Thank you, everybody, for coming.
Yeah. Thank you.